Josh Judd, he's been a leader in IT industry for over 20 years, roles ranging from senior Unix system admin to mechanical engineer, machinist, programmer to best-selling author to chief architect and CTO. He helped create storage networking industry. He wrote numerous storage-related patents, invented and created. You did a lot of stuff.
I did stuff.
It was awesome. Josh, CTO for Warp Mechanics, stun and amaze us.
Josh.
So anyway, I'm Josh. We only have a few minutes and I don't want to stand between people and lunch, so I'll try to go through this in a relatively expeditious manner. Briefly, I'm going to review Lustre over ZFS. Warp and Livermore have been talking about this for a long time, and at this show we also have other vendors talking about it as well. The community for Lustre over ZFS is greatly expanding. I will very briefly go over the Warp platforms we used for these solutions. I would just encourage you to come by the booth if you want more information about it. And mainly I'm going to discuss 3 case studies of how Lustre ZFS hybrid SSD solutions worked in HPC style environments, what the actual use case was and why we think it's a good idea. This is a complementary talk to the Oak Ridge SSD talk that's going to be happening after the lunch. So please stay tuned for that one as well. So in a Lustre ZFS solution, ZFS replaces the LDISC FS layer, but it also, in our solution, replaces RAID. So we have a fully integrated Lustre ZFS solution where the ZFS layer is the data protection. It is providing advanced services like compression, replication, if you like, then provisioning, deduplication, and so forth. So it's a very feature-rich RAID layer, but it runs purely in software on the same controller that runs the OSS. So you no longer need a RAID layer and an OSS. You have a RAID OSS, all of which is running open software. And the code has been proven quite scalable in Livermore's environment. I believe they are in the process, as I understand it, of replacing all of their non-ZFS systems with ZFS systems. So it's been quite a success over there. And we've also been implementing this in other HPC shops and high-performance business computing shops and having good luck with it. So how does this relate to hybrid SSD solutions? ZFS includes something called the L2 ARC, or Level 2 Adaptive Replacement Cache. This is built into ZFS. It's not something that's a Warp unique feature or something we charge you for, but bottom line is you can use SSDs as a transparent to Lustre cache, and we will only fill them up with data that is likely to be read again. We've found that there are kind of 3 distinct scenarios for the L2 ARC in high-performance computing. In one case, you just use a tiny bit of it to cache frequently read metadata. ZFS allows you to tell it what the L2 ARC is allowed to cache. And you can say, don't cache the data, just cache things like, inodes and so forth. This can greatly speed up LS, for example. That kind of thing. Medium-sized L2 ARC is good for general purpose workloads, kind of a mixed workload, like if you have user data intermixed on a file system with your checkpoints and other more classic HPC stuff. And possibly more interesting scenario, the large amount of cache for analytics workloads. If you're going to run an analysis style workload on a Lustre file system, you really want small reads to go fast. particularly because a lot of programmers are not necessarily great at it. So we get customers who come to me and say, well, you know, we've got this Lustre file system that has, you know, 4 billion 4K files. Well, that sounds like a bad idea, but okay. The more of that you can get onto the SSDs, the better off you are in many, many ways. So L2ARC does only one thing, which is read acceleration. Obviously, you can't read anything from it until it gets populated. So how does something get onto an L2ARC? Well, if data is in the primary ARC, RAM, and it's about to get kicked out of RAM because RAM is full, ZFS looks at it and says, do we have some reason to believe somebody's going to want to read this again ever? If so, I'm going to evict it onto the SSD instead of evicting it into the bit bucket. So ZFS will cache as much as possible in primary RAM and then kick stuff out onto the SSDs if you're likely to need it again in the future. And a similar kind of lookup happens when you're reading. If it's in RAM, that's where it will be serviced from when you're reading from the file system. If it misses the RAM cache, then it'll look at the L2ARC and see if it can get it there, and if not, it'll go off of primary storage. The important point here is that L2ARC is completely optional in terms of being able to answer a customer's inquiry. If the L2ARC SSDs all simultaneously fail, your system will go slower, but it won't stop. You don't need any redundancy at the L2ARC level. Okay, we used 2 platforms to do testing related to this. Our big platform with lots of hard drives and a few SSDs. Come over to our booth, I will be happy to explain it and show it to you. We have one, it's the one with all the blinky lights. And our SSD-optimized platform, which can, contain 120 terabytes of pure SSD if you would like to do that. It's 2U60 SSDs, dual controllers, and it runs ZFS plus Lustre in a complete integrated unit. Okay, enough vendor pitch. What did we actually do with the stuff? First thing I find useful about this is if you can separate your checkpoint style I/O from general data. Let's say in an ideal universe you have your Lustre file system and all it does is checkpoints. It becomes 99% writes, 1% reads. And yet somehow I keep getting these RFPs and RFIs saying, we're 60-40. We're 60% writes, 40% reads. Well, you seem to be restoring an awful lot of checkpoints, right? No, it's one file system that's an intermix of different data types. That's the most common scenario we get. So if you can point your checkpoint style data at pure hard drives and then point your general purpose data at something that's got these SSD accelerators, you will get A, better read performance for the general purpose data, but also B, better write performance for the checkpoint file system. Anytime you're interrupting this nice smooth motion of writes in the checkpoint operations, it keeps getting interrupted by the thrashing around of the reads. So if we're responding to the reads using the SSDs, we don't have to mechanically move things around to interrupt the writes, if that makes sense. Okay, this is not entirely predicated on you being able to separate your workloads, however. You don't necessarily need different mount points to do this, because ZFS is smart enough to not cache the checkpoint style data. If data is written into ARC and nobody ever reads it again, it says, how frequently was this data accessed? The answer is 0. All right, I'm going to evict that into the bit bucket instead of evicting it onto the SSD. So you can actually bolt these L2ARC SSDs onto your complete file system and it will automatically only cache data that somebody somewhere has read back at some point. And in deference to time, I'm going to go through these relatively quickly. Analytics. So I have several people who have life sciences or genomics or RNA style use cases where one writer may be pushing data into a file system. It could be a sequencer with a Samba mount that's pushing data directly onto the file system. And then multiple readers will have to read back that data, think about it, write a derivative. And then multiple readers will have to traverse all of the derivatives and compare them to other things many times. In this case, you're not exactly getting a classic HPC workload. And we've found that a large number of SSDs, or a large ratio of L2 ARC to primary storage, is perhaps appropriate. But one of the advantages of this is that if your workload shifts periodically, we will automatically age stuff out of the SSDs. So let's say you're filling up your file system with sequencer data, and you're analyzing the heck out of it, and then it gets gradually less relevant over time, but you don't want to delete it or archive it off the file system. As you access it less often, it will just tend to fall off the SSDs in favor of more recent data. Okay, what's the deal? Working set. If your application has a working data set, then it's conducive to this kind of SSD cache mechanism. Let's say 20% of the data in your file system is currently being analyzed and the other 80% less active, right? Then you just create a ratio of SSD cache to primary storage of 20% cached, and it just kind of works out. The more aggressive scenario, we've got some HPBC customers, high performance business computing customers, who are doing analysis of financial data. And they actually use a 1-to-1 ratio of SSD to primary storage. So if you've got, a petabyte of disk, you would also have a petabyte of SSD. In reality, they don't need a petabyte of disk or SSD for this particular solution. It's like 200 terabytes. But still 200 terabytes of SSD cache and 200 terabytes of usable space in disk. Well, why would you do this? Why not just build the thing out of pure SSD at this point? Well, it actually goes faster, because when you're reading off of L2 ARC, you're reading off of what amounts to a RAID 0. So you don't have any parity overhead. You get to use every SSD spindle, quote unquote, that you paid for. So for a given amount of dollars, you get more throughput out of a non-protected array of SSDs. And the SSDs are so much more expensive than disks that if you don't have to buy parity SSDs, that saves you enough money to buy the hard drives to back them up. And you end up never actually reading from the hard drives except in a failure case. They just act as sort of an HSM layer or a backup, I guess you could say. And 100% of your reads are going to be cache hits. So if you're traversing this 200 terabyte store repeatedly, trying to get ahead of your competitor in making the best stock trade, then getting that last little bit of performance is definitely the way to go. And they certainly have that small read problem, right? Everything is 4K reads. So having everything in that scenario it's like 99% 4K random reads, which is not normally something Lustre is great at. But this, now it works pretty well. Just as a little side note, since I still have about 60 seconds left, this particular customer started out doing that via Samba. So, an HPC workload over Samba is not necessarily the most optimal scenario. And we found a whole bunch of exciting new ways to break Samba. If you have several thousand cores all pointing at a single Samba server, so we blew it up with out-of-memory errors, we blew it up with Samba core dumping, we blew it up 6 ways from Sunday. Eventually, we ended up saying, why don't we do this? If only you were doing Lustre, this would not be happening, because Lustre's good at having lots of clients talk to one server and not coughing up kittens, as they say. So we created a CentOS layer on all of their Windows machines and put a single Windows server instance as a VM in that CentOS, KVM. The CentOS layer becomes a Lustre client, and the Samba is served from the virtual machine manager to the single VM. Now you only have one client per Samba instance, much more easy to scale. As you add more clients, you also add more Samba servers. Obviously, we wish that there were a Windows Lustre client, then we wouldn't have this kind of kludgy workaround, but at least it doesn't crash now. So just to wrap up, our, I probably should have changed that first bullet. Oak Ridge is going to present some findings later that I agree with, but the talks got reversed and I thought I was going to be after there. So I'm agreeing in advance with my friends at Oak Ridge about their findings. As such, I found that the optimal use case for SSD in HPC was a hybrid system and not a, for instance, pure SSD checkpoint file system or anything like that. But stay tuned for the details from my good customer, Oak Ridge National Labs. If you want more detail on that, since I'm now out of time and it is time for lunch, I would suggest popping by our booth in the vendor area anytime during the show. Thanks.